All right. Good morning, all. And as you can see, Letiția has kindly agreed to come back. As a true scientist, she likes to finish whatever she starts, at least the important endeavors. And Letiția, very happy to have you back.
Hello, everyone. Good morning. Thanks for having me back, because indeed I would like to tell you the things that have happened since 2020 in the LLM space that have made transformers reach really the ChatGPT caliber and brought LLMs into everybody's mouths and hands and into the press. So we have talked last time about the transformer architecture. And we have now said, okay, we have these architectures, the encoder, decoders, encoder, decoders. And for large language models, currently, we use transformer decoders to train on the entire internet. And then hopefully, after we have learned language, we can solve with that knowledge about language, everything else. And a huge topic that has really made LLMs what they are today is the topic of prompting. And prompting is usually regarded as a, non-technical, non-mathematical job description. You have maybe heard of the notion prompt engineer and so on. But what I think I could convince you about today is that the idea is exactly that after we have done the effort to have written a transformer decoder in code, to have defined the loss function, to have done the training for many months on many GPUs to train on the entire internet, after we have overcome spiking gradients, after we have overcome diverging loss functions, we don't need to do coding and math anymore. We can just program in natural language, namely by using words. Because let's suppose we have trained this huge transformer decoder on the entire internet, but now, and we make the statement that LLMs trained on the entire internet are capable of many tasks. And as I motivated last time, it is to be expected because language talks about the world, and these transformer decoders train on language. So by transitivity, a language model will be able to know some things about the world. Maybe not everything, but impressively many things. And if you want to predict, for example, that if I hold an apple in my hand and I will open my hand and the apple will fall, and if it will say fall and not fly away or do other weird things, then there is at least some understanding. It's of course debatable how much understanding there is, but some understanding is there. And we want to find a way to get this understanding out of the model and make it reach the level of ChatGPT. So let's suppose I want, I want some information from it, so I can only let the model do what it was trained to do, namely to complete sentences with other sentences, to write entire paragraphs. So, to predict the next most likely token given the previous tokens. So I will just ask it this question: when was Albert Einstein born? Now let's play a game. You are the language models, and I have given you this question. What do you answer? And you don't have to be the smartest language model out there, so you can just say, for example, centuries or millennia, or give a fuzzy answer. But what would you say? What is the answer you would give as a large language model trained on the entire internet? Yeah? And where, you're a smart language model, because what I expected from, a language, so what I expected you to say is to complete with the right answer, basically what you expect from when you give this question to a model. But what you did is exactly what I wanted to say, that is also possible to complete a question with another question. You asked, where was his hometown? I could ask, I'm a different language model, I would say, when was Heidelberg born? Because an enumeration of questions is a thing that LLMs have seen in the training data set, because exams were in the training data set. Exams are enumeration of questions without answer. So somehow we can also continue a question with another question. I could continue the question with, this question will come up in the science history exam. Yeah. So somehow, what I would expect from a language model would be this. That's why I actually asked the question. But what the language model just doing what it was trained to do, namely to complete the next tokens given the previous tokens, these are the previous tokens, these are also likely answers. And how to avoid the model giving these answers and enforce it to give this answer. That is what prompting is about. So let's prepare for the greatest idea in scientific advancement in natural language processing since 2017, namely that we want to ask the model nicely to do what we want it to do, namely via prompting. Prompting is just a way of presenting the input to the model in order to increase the probability of the expected answer. So the model could predict anything, but we want to increase the probability that the next most likely token for the model is what we expect as an answer. And how would we do this before LLMs? So let's say I have a task lying around called natural language inference. And you don't have to know what natural language inference is, when maybe the LLM also doesn't know what natural language inference is. And for this task of natural language inference, I have a CSV file run on my computer, which stores these kinds of sentences like premise, John ate pasta for supper, hypothesis, John ate pasta for dinner, and 2 rows with such sentences. We have labels attached, which can be either entailment or contradiction. And in classical NLP, with classical neural networks, I would train a neural network specifically on these sentences, on sentences like these, with labels like these. And after I have done this training, I would test on sentences very much like these, and the model could do just this task, nothing else. Yeah. But with LLMs, it's exactly the other way around. We have trained on the entire internet. We have information about language. The model knows what maybe the word premise means, what John is, what pasta, no, not who John is, but that John is a named entity, what supper means, and so on. So let's just ask this. Let's just give this example to the model. What would it say? So now let's pretend you are the language models. What would you say? Would you even know how to go about this? Like if I just give you this sentence, what would be your next token? Any good guess? Would it be, yeah? John. Okay, yeah, that's a good one. I mean, it could be any other one. And that's a problem. It could be anything. Yeah. So let's invest a little bit of my expertise of a person that knows what natural language inference means, and just ask the question differently. We verbalize exactly the same sample, just differently, by saying that suppose John ate pasta for supper, can we infer that John ate pasta for dinner? Can you answer the question now? What is the next most likely token? Can you? Probably. Right? I mean, you know a little bit of logics, and if I ask it like this, saying yes or no, then the likely token is yes or no, and not maybe, perhaps, or you could continue this question with another question. So what we really did here the probability that the next token is the right thing was maybe 1 over 10,000. So let's suppose there's 60,000 tokens in our vocabulary. 50,000 of them are super, super, super unlikely, but 10,000 of them are super likely still, because we have formulated the question badly. Now, by formulating the question better, with, let's say, we have increased the probability to 1 over 20. We reduced the possibilities of what the next token can be. And now, by just adding yes or no, we increase the probability even further to 1 over 2. So now it's a 50-50 chance that the model will produce in its training regime the next most likely token. This is basically the magic of prompting. Before, in machine learning, people were doing maximum likelihood estimation, they were doing expectation maximization, and many weird algorithms that were automatic to somehow increase the probability of the data given the model. But now we do it with just words, and this is a significant increasement, and whether the model can really do something useful with this 1 over 2 probability and to really give in a 50-50 chance possibility the right answer, of course, it needs during pre-training to know that what John might refer to, that supper is a synonym for dinner, what supposing means and what inferring means, yeah? But this is how we elicit knowledge from the model, by just asking the question nicely, in the sense that we increase the probability that what the model will say is what we expect it to say. And of course, there's many other ways to do it. There's not just these ways. There's maybe an infinite possibility of ways to ask this. And that's why, I mean, there's this job description of a prompt engineer that finds such good prompts. Okay, but if we're unhappy with that, with what I will call vanilla prompting, so vanilla prompting means we have a weird sample that, let's say, not even a human might know how to solve it. Prompt engineering means that we take the sample, we present it somehow, we infuse our information about the problem and tokenize the question. We have the huge language model that will predict hopefully the right answer, and that's vanilla prompting. But you know, sometimes we're lazy and don't want to invest all this effort, and a more machine learning way to do it is basically without a human in the loop. Just with the programmer in the loop and stochastic gradient descent, we can keep the example as is, we can tokenize it, and of course the language model will be unlikely to produce the right question. But what we can do is to just append some vectors, and it's a little bit of a hyperparameter how many vectors we append. And these vectors don't correspond to any token. Yeah, these vectors correspond to tokens, and tokens correspond to subwords, as we have learned about tokenization last time. These vectors don't correspond to anything. They don't map to words anymore. But we tune them with stochastic gradient descent on a few examples to make these until the model will deliver the right answer with them. And this is called prompt tuning, and these are soft prompts. They're soft because they don't so language is crisp, language is very symbolic, but these are continuous vectors. That's why they're called soft prompts. And that's how we can do it. And here, basically, we are tuning in word space. And of course, we can tune with a human. We could tune also with a discrete search. Here, we're tuning in the word embedding space with stochastic gradient descent, like we're usually used in machine learning. And if this reminds you of adversarial examples repurposed for good, then it's a good reminder to have. But I don't know if you have the knowledge of adversarial examples. This was just a reference. OK, so these were two types of prompting. But there's even more powerful types of prompting. And one I would really like to talk about is the so-called in-context few-shot learning, because it's, again, something that that people might not necessarily understand why this works so well. But it's, again, prompting. So we basically increase the probability that the model will produce what we expect. Yeah? And how can we do this? Let's say we have the task of with a lot of sentences, and we want the model to say whether these sentences express a positive, a negative, or a neutral sentiment. And what we can do is to show the model in the input, just append these prompts of solved examples, so sentences with the right label. And then if we're interested in testing, in knowing about the sentiment of this sentence, then the likelihood that the model will produce the right thing will increase tremendously. And people like to say that this probability here is increased, that the model will say positive because the model's understanding or reasoning is elicited. I don't like these words because they're synonyms for magic. And I don't like magic. What is magic? So the idea here is that, again, we are restricting the solution space. So we're increasing the probability from 1 over 60,000 to 1 over 3. Because what is kind of obvious from the input pattern here is that after // the only possibilities that we would like are positive, neutral, and negative. Yeah? So now we have increased the probability of the model doing the right thing to 1 over 3, which is tremendously more than 1 over 60,000. And then, of course, for the model to choose the right thing in a 1/3 probability setting, it requires knowledge. So it has to know what the word improve means. But we hope that this was something that happened during training and that the model knows that. And to bring even more arguments to the fact that it's this, structure, it's this pattern that makes it clear that we expect just 3 labels, makes for this weird efficiency of in context learning is I reference this paper as an argument. Namely, what they do as an experiment is they do in context few-shot learning, so they show examples to the model, but mess up the labels. So instead of saying the correct label positive here, they say neutral, for example, and instead of saying neutral, they say negative. So they still have this structure, but the labels are messed up, and in context learning still makes the model more likely to give the right answer. Of course, in context learning is much better if you give the right labels, but even if you give the wrong labels, it's still increasing the probability tremendously. Yeah, this is one argument for this unreasonable effectiveness of in context learning, that is just a specification of the label space. But there is also a little bit of another argument which goes a little bit again into this camp of, I mean, let's bring it back to normal machine learning. In normal machine learning, what do? We do SGD by we update the parameters of the model with stochastic gradient descent to increase the probability of the observed data, of our training data. And basically, we have two ways to get to better likelihoods. So one way. So why are we doing deep learning in the first place? We're doing deep learning such that we can start with bad representations and get better representations in the end that will give us the right answer. And we can do it in two ways. One way is normal stochastic gradient descent. So we update the parameters, so the feed-forward network parameters, the self-attention, the query key and value producing matrices, the position embeddings, and these embeddings along with stochastic gradient descent until this representation becomes better and will deliver the right answer. That's one way to do it, very deep learning way. But the in-context learning way is say, let's keep the parameters fixed, but we will append stuff to the input. So we will have here additional input, additional examples. And what will happen then? We have this additional input. This will go into the self-attention. So when we compute this representation here after self-attention, with this additional inputs, the self-attention output will be different as if we didn't have this additional input. So we didn't change this representation by changing the parameters of self-attention by updating via SGD, but we changed this representation by just giving more input to the self-attention layer, which will then compute different attention scores and will combine into a different representation. And once this representation is different, this will be different, and this will be different, and with in-context learning, it might become better. So yeah, that's basically the one interpretation why in-context learning is so good. And there's a paper basically entitled something like about the equivalence of, or why in-context learning implements SGD, if you want to read even more about this. But yeah, this was the idea of in-context learning, of few-shot in-context learning. Are there any questions regarding this or prompting in general? Yeah. If you promise what? A better reward? Money, yeah. If you promise money, then it will be better, yeah. Mm? Yeah. Exactly. So what we can do is exactly to look at the activation that these prompts will cause. And then we can store that activation, because that activation somehow is now a direction which makes everything for the better. And we can store that and call it a steering vector, and then add it to the representations without adding any more input and so on. But then this will control the model to behave in the way we want. Yeah, these are called steering vectors. I mean, it's not about, so we're not making the promise in the sense that we will really give the model money. So it's not expecting any money. What it's expecting is, it's just predicting the next most likely token given now money tokens. Yeah. So if we do steering vectors, no, I mean, we determine the steering vectors from nice prompts, so it's still nice prompts. So we can do nice prompts, we can do steering vectors, we can do stochastic gradient descent, whatever helps us get the answer better. But the thing that's very cool about prompting is that I can do SGD, I can do steering vectors, my mom cannot do that, but she can do prompting. So that's the cool thing, that now we can program in natural language to do what we want to do. Yeah. Okay, thank you. Good. It's not over with prompting because, you know, since 2020, there were many years in machine learning. So let's get ready for the second greatest idea and scientific advancement in NLP since 2017, since the transformer was invented, namely to append the prompt, let's think step by step, and write an entire paper about it. So again, it's an unreasonably effective prompt. So let's talk about it, why this happens. And I'm a little bit tongue-in-cheek about people writing an entire paper about just this single prompt. But the idea is that at that time, when that paper was written, people didn't expect this to happen. So if people would have told the scientific community, let's think step by step, they wouldn't have taken it seriously. So of course, writing an entire paper with many experiments and trying it out with many models, that was kind of necessary. So let's think about it. So what does this let's think step by step mean? Well, it's again a type of prompting. It's called chain of thought prompting. And the idea here is the following. We ask a question to the model, and this question doesn't have an immediate answer that can be retrieved. It's not when was Einstein born. It's a more complicated thing that requires, you know, problem solving, and it's even hard for people to come up with the answer right exactly after the question was put. So maybe you require a sheet of paper and, you know, or to think a little bit, you do some little math steps in your head. So let us let the model do that too by adding let's think step by step. Yeah, because if we don't add let's think step by step, kind of the thing that we expect is exactly the answer directly. So by adding let's think step by step, we let the model not answer directly, but have a little bit of a detour into breaking down the problem, and after it had brought down the problem, it will eventually answer. And if it doesn't answer, we can prompt it again and say, hey, what's your final answer? And it will say final answer, and it will be 9. So again, I mean, is this reasoning? Is this thinking? These are, again, words that hide a little bit what's happening, because what's happening is we're predicting the next most likely token given the previous tokens. That's what these models were trained for, not for thinking, not for reasoning. So the problem is here broken down into smaller pieces, which allows the model to do some divide and conquer. But this divide and conquer will work only if the model already has the knowledge to do all this breaking down. So just by adding let's think step by step, it's not like we're teaching the model to think or anything. So if this knowledge is there, let's think step by step will work. And we think that this knowledge is inside the models because the models trained on the entire internet. And on the entire internet, there's many math problems with explanations, right? Think of textbooks. Yeah, we can just elicit that knowledge by adding this. And again, because it's next token prediction, when the model finally arrived at the point of giving an answer, basically this token becomes way more likely because we have broken down, so it has broken down the problem into 3 plus 6, which is 9 is a way more likely continuation to 3 plus 6 than to this question. Yeah, so this is a little bit the reason for why chain of thought prompting works, and it works out of the box. It of course can be reinforced via training and so on, and then this will become even better, but there's not really much thinking or reasoning happening here other than we're just letting the model exhibit a behavior that it has learned from reading textbooks on the entire internet anyway. Yeah. Are there any questions regarding in context, chain of thought prompting? Because we will get into the final way of doing prompting, which is retrieval-augmented generation. And there's a question. Yeah. Yeah. Yeah, it's called common crawl. So the question is how do we train on the entire internet? There's something called common crawl, which, what is a crawler on the internet? You start from a web page, and hopefully a web page that has many other sublinks. So Wikipedia is a great place to start. And you start on Wikipedia somewhere, you read Wikipedia, you find the link. That's what a crawler does, not a model. You find the link, you click the link, and you will open another web page. And that web page will have a lot of links, and you open all of these links. So you see it's a very exhaustive search with a lot of branching. But by doing that exhaustively, and it's very computationally intensive, by the way, you crawl the entire internet. So all the links that have been ever linked onto some other websites, you will find them. And of course, there's parts of the internet that are not linked anywhere, and that you will not reach. But yes, you literally train on anything that has been linked. So I know for sure that my website has been crawled, because if you ask ChatGPT who I am, it knows. But why does it know? Because I have websites. So it's really a lot of textbooks and a lot of archive and a lot of scientific material that these models have read about. So that's not to be neglected. Okay, but that's cool, because now we're coming to retrieval-augmented generation, which is exactly a way to handle the situation where the model didn't read about anything. So let's say it didn't read about my website, so because maybe I didn't have a website. And here I thought of an example of, we might ask to the model, how many employees did NVIDIA have in 2024? And this is just so I invented some numbers and some companies for illustration purposes, but let's say I have this curiosity, I ask it to a language model, will it be able to give me the answer? And the question is a little bit ill-posed, because these models have been trained on the entire internet, but they have been trained, let's say, in 2023. Things have evolved since then, so it doesn't know exactly what has happened in 2024, it just didn't read that internet. And maybe the requested information is not public. I don't know, I have no idea, but let's assume it's not public and I still want to know it. So how can we go on about this with retrieval-augmented generation? The idea is to use this prompt, to use this question to do basically a search. Imagine any semantic search when you're writing on Google something. We search for related passages in company internal documents that NVIDIA might have in a database. And if we do this search, we append the retrieve passages that hopefully are relevant to the question that I asked, because that's the retriever's job, and append those passages here in this color to the input and ask again. Yeah? And now, if the company internal documents contain that information, it will be written maybe that it reached 2,000 employees, it's an invented number, and the model response will be better. Yeah? So this is a way to handle missing information from tree training, and it is a widely used prompting technique in industry, because in industry you have a lot of company internal documents, and language models don't know about that. Great. That's very in short about RAG. Of course, there's many details to how to make the search work well, but yeah, I won't get into those. Yeah. Of course, yeah. There are issues, and that's why we will come to post-training. So there are issues into reading every web page, because you know what happens if you scrape the entire internet and parse the HTML text for text. You will end up with a lot of download buttons. So your training data will be download, 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 because there's just very, very, very many web pages that contain the word download. And what you, of course, have to do is you scrape the entire internet, you filter the data, so you exclude anything you don't want, like entire passages which are just slash, 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 or download, 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 download. And it's an entire art of cleaning data. If you want to read about it in a very nice scientific blog post, it's called Fine Web from Hugging Face. They have really kind of released the way in which they do this data cleaning, but of course you have to clean that entire internet because most of it is not necessarily the things you want, and sometimes when you prioritize what you read, of course you should read Wikipedia, you should read news articles and things that are highly curated, and then if you move into the darker corners of the internet, you have to be careful of what you take and what you not take. You have to do language detection, because the internet is not just English, and if you're interested in training an English-only model, you should want to exclude every other language. If you want to do it multilingual, then you include all the languages. So yes, it's an entire art to training on the entire internet. That's why pre-training is so hard, and that's why just very few companies do it. Yeah. Cool, but that it was it, basically, the summary of types of prompting, and I hope I have convinced you what the power of prompting is, that we don't, I mean, we can still do SGD, we can do weird activation, patching, and steering vectors, and so on, but we don't need to, because this is what made ChatGPT usable for everyone, because I can do SGD, you can do SGD, my mom cannot do SGD, so she can do these things, maybe not RAG, but she can do these things and interact with these models. And this is very powerful. And, but yeah, I mean, sometimes these things don't work well very out of the box, and there must be some post-training to even help these things get better. But before going into that, let's play a small quiz. I don't know how much you read machine learning papers, but I hope you will see a pattern emerge here, and you will see the point I'm trying to make. Do you know which large language model was presented in the paper Improving Language Understanding by Generative Pre-Training? Yeah. Yeah, well, you're smart. So yeah, GPT-1, this is GPT-1, yeah, GPT-1. This was in the GPT-1 model. Then language models are unsupervised multitask learners. Do you know what model was presented in this paper? Yeah? No, but Llama came much later after than this, but good guess. Multitask learners. I spoil it, GPT-2. Then the next one will be super hard. Language models are few-shot learners. Think of iteration, or like this was GPT-1, this was GPT-2. What do you think is this one? Yeah? Iterate one down, GPT-3. But good guess, good guess. Unfortunately, there is, oh, I won't spoil the next one. So what is the next one? What do you think? GPT-3 is this one. But you're almost right. Just it's not GPT-3, it's not GPT-4, it's GPT-3.5, also called Instruct GPT. So yeah, these are the answers. Unfortunately, there is no real GPT-4 paper, but yeah, I mean, here OpenAI has stopped teaching the world about the things they do. But why I have put these titles over here is that you can kind of very well see how these things evolved. So in the GPT-1 paper, the transformer decoder, so this GPT, this generative pre-training, was introduced. Here, transformer decoders. Here, people have realized, oh, if we train on internet-scale data, we can do multiple tasks. So exactly this idea that we have learned language, and language talks about many things in the world and about many tasks applicable to the world. So GPT-2. Then, few-shot learning. This is, you know, the in-context few-shot learning prompting technique that I've been talking about. So with GPT-3, with even larger scale, you can get these prompting very well done. But then to do these models even more sensitive to prompting, you have to do something like following instructions and human feedback. And this is the final piece of information that we need to know about how to make ChatGPT. And these are post-training techniques. So instruction tuning and preference tuning with human feedback are things that we need to do after we have read the entire internet to make the model even more likely to produce the things that we want it to produce and less likely to produce the things we don't want to produce, and even without prompting, yeah? So somehow to make these models behave like we want them to behave. And let's take the idea of prompting. Here in prompting, if we want to increase the likelihood of this completion, we might do it the following way. We can say question, when was Albert Einstein born, answer, and then after these dots, of course, we expect an answer. But the model will not necessarily be super sensitive to this, and we want to increase the sensitivity of the model to this, and this is called instruction tuning, because you can think of prompts, these prompts, as of instructions, like question, answer, and we want to train on these instructions. So instruction tuning is basically the idea that we fine-tune. So we have done all this internet scale training of next token prediction, and now we again do next token prediction, but on a very curated set of data called instruction data, where the idea is to scrape all benchmarks and databases that people in NLP, in natural language processing, have established over the years, take those and train on them. So let's take one example of machine translation. Machine translation means that you're translating from one language to another, and let's say we're translating from English to German. And before, in pre-training, what would happen is that this sentence, the cat sat on the mat, and the German version, die Katze saß auf der Matte, just was lying around on the internet, and then the model could have learned to translate, but wouldn't have known how to give you that knowledge because it didn't know that it was translation. So now we kind of want to teach the model, well, this is translation that you do now. So we just append this instruction, and of course it's written by humans. Please translate the following sentence from English to German, and then we can take this sample from machine translation and append it. And very important, we use the exact pre-training objective of cross-entropy, of next token prediction, but now on this entire thing. And it's fine-tuning because we do it after we have done the pre-training, but it's just supervised fine-tuning of repeating and parroting exactly this sample. And we can do it for one task, but of course it works very well if we do it for all the tasks. So we can do it on question answering. Please answer the following question, and then we give it the question, we give it the answer, and it has to parrot all these things. On chain of thought, we can even give it examples from textbooks where there's this chain of thought inside, like you have the reasoning before giving the answer, and so on and so on. And you can imagine that the more tasks you add here and the larger instruction data set is, the better. And this is where, you know, scraping the internet is easy in the sense that you just need a lot of CPUs and a lot of storage space, and you will eventually be able to do that. But here you kind of need experts to scrape natural language processing benchmarks, or even additional annotators to write you even better examples for this. But it's still supervised fine-tuning in this post-training fashion. And just to give you the examples of how much this brings us, on the y-axis, you can see the likelihood that the model will say, I like this answer that the model has given to me. After you have done only pre-training, the likelihood, I mean, people like it, but not very much. If you prompt it, they like it better. And the larger the model, if you go to 175 billion, the more they will like it. But especially with smaller models, prompting will get you this far. And then if you do this supervised fine-tuning, this letting the model parrot some instruction data, it will get you even further. But to really reach the last bits of, let's say, the things, to reach everything that we want to make a chatbot, human feedback is needed. Yeah. So what is human feedback? How can we train with human feedback? And again, this is, before we were training on the entire internet, very self-supervised, without a lot of human annotation. Here, the human is again in the loop, and we kind of need to pay annotators if we want to do this. So the idea is to collect a data set composed of triplets that are, so we have the question or the task, like, for example, let's translate from English to German, or please answer me the following question, and then you give it when was Einstein born. And then you generate a possible answer either with a pre-trained language model or with a human. Yeah, actually with humans it works even better. But so you generate it, you somehow produce an answer, and then you produce another answer. Okay, and after we have done this, you employ human annotators and let them rate whether given A, given the question, they prefer B or C more. Yeah, and then you get the thumbs up for one answer and the thumbs down for the other answer, because they have to choose which one they prefer more. And maybe you have seen the thumbs up and thumbs down in ChatGPT interface. Well, you're doing that. That's what you're doing when you're giving thumbs up. Just so you know, you're annotating, you're doing labeling day. Okay, so, and we have this human feedback. This is literally feedback. And now we can train with either reinforcement learning from human feedback, which was the first way to do it, but it's a little bit complicated because it requires reinforcement learning, and we don't know about reinforcement learning yet. So I will present to you in more detail the other version to do it, human feedback tuning, which is called DPO, or direct preference optimization. And if you ask why what the difference is between them, well, it's just difference of what technique you apply, but their optima are the same. So with reinforcement learning and with DPO, we will, if everything goes well during training, you will converge eventually to the same thing. So what is DPO? So let's assume we have this question, where was Einstein born? An LLM or humans, doesn't matter who, said that, look, these are two possible continuations of this. Humans have annotated, I like this more, I'd like this less, and now we want to train on it. And direct preference optimization just says that we train the LLM, again in post-training, yeah? So we have the LLM that has been trained on the entire internet, and in a supervised way, we train it to increase the likelihood of positively rated answers and decrease the likelihood of producing these negatively rated answers. And at the same time, we have a regularization term to enforce the model to, in predicted probabilities, to stay close during training. The model should stay close to its original version before it started all this preference tuning. So somehow we train the model to do something to increase the likelihoods of behavior we want, decrease the likelihood of behavior we don't want, but at the same time stay close to its original version. Why are we doing this? Why do you think we're staying close to the original version of the model? So we kind of want to train, but not train too much. Why? Yeah. Exactly. So to avoid catastrophic forgetting, it's called. It has a very dramatic name. Catastrophic forgetting is when it forgets by training on this very specific data, on specific words that people have come up with. We could train on this, but to the detriment of everything else, what it has learned during pre-training. But we don't want that. We don't want to forget all the Shakespeare and all the archive papers it has read during training. So that's why we regularize it. So let's go into the loss function and look exactly how this is done. This is a loss function. I'll explain it, but just for reference, this is the normal cross entropy loss function that we use in supervised pre-training and in instruction tuning. And now the DPO loss function is kind of similar, but a little bit different. Because what are we doing now? We're not having just one thing the model needs to parrot, but what we want to do is we want to increase the likelihood of these highly rated answers, decrease token via token the likelihood of these answers, and regularize to stay close to the reference model. And the reference model is the model before it started training in the first place. So after pre-training. Yeah, and if this is supervised learning, you can think of this as contrastive supervised learning, yeah? And this is a very simple way to do this training, and I'm a little bit still confused of why people came up with reinforcement learning in the first place to do this. But yeah, I mean, this is contrastive supervised learning, and I'll just tell you just briefly about what RLHF is all about. RLHF, why do we even need, why did people even think of reinforcement learning where there is you can do the same thing with a contrastive loss? Well, the idea is here that you train the LLM to produce outputs that are getting high ratings. But here, we don't say we increase the likelihood of this or we decrease the likelihood of that. We just let the model produce anything that increases the likelihood, that will get high rating eventually. So if the model will be able to produce anything, the model has to produce text. We cannot stay in probability space. It has to make a choice for a token such that it can then choose the next token and the next token. And because we're choosing from probability, from the continuous probability space to the very discontinuous text space, we're doing an argmax. And an argmax is non-differentiable. And to overcome the non-differentiability, you need a framework that does exactly that, overcoming non-differentiability, and that's what the reinforcement learning comes in. But yeah, this is the high-level idea of RLHF. And this came before DPO, but they're solving basically the exact same objective. So how you can imagine this human feedback training is that we have a model that has the entire internet, which is full of Shakespeare and archive papers, which are nicely formatted, but it's also full of toxic behavior. Just think of some social media places. And we want to discourage the things we don't want, and we want to encourage the things we want. And yeah, this is the idea of human feedback. Now, just one more thing I want to tell you about LLMs, which is a little bit about benchmarks. Like, I mean, there are these LLMs, they're good and so on, and But to know that something is good, you have to test that something is good. But there's a 1-year cycle of madness, which kind of looks like this, that people design a super hard benchmark. Then some companies spin up their GPUs and train on more data, larger models, and on cleaner data than ever before. And then a few $1 billion later and a few months later, the super hard benchmark was solved, and then you go to 1. This is basically the circa 1-year cycle of madness. And I don't have to tell you that these models can do things. So you have played around with ChatGPT. They can do things that you couldn't do before. They can even explain jokes and so on. I want to come a little bit into the discussion that, there's this lesson that if we scale up to more and more parameters, the model will become better and better. And this is a fact, indeed. If you scale to more parameters and to more data, you'll become better and better. But even if you keep the data fixed, just increasing the size already will get you better performance. And there's a lot of benchmarks on which you can test, like, for example, on understanding English proverbs. This is the human baseline. This is what the 8 billion parameter model can do, a 62 billion parameter and a 540 billion parameter. And while on some benchmarks, if we have trained these two models, we can kind of extrapolate by linear extrapolation what this model will do. On this data set, it's scary, right? Here we have performance, here we have another performance. If we linearly extrapolate, we think we land over here, but the actual extrapolation here is non-linear, and people call it this is a problem. People call it emergence and think that AI will take over the world, because who knows what will happen in terms of capabilities when we look at the next model, because this is unpredictable, this is predictable. Yeah. So I want to a little bit counteract that fear, because if you look a little bit into more detail, this emergence here is a little bit counterintuitive, because what do we people who train these models look at during training? Usually, you don't always look at these things, but you always look at loss, at the cross-entropy loss of predicting the next token. And this is a logarithmic scale, so if you look at this curve, it's actually diminishing returns that you get. If you look at the probability of predicting the correct next token, this is not emergent, this is not nonlinear in any way. But somehow, if you test on logical questions and on English proverbs, it becomes emergent, right? You have this linearly not extrapolatable curve, which is a little bit of a problem. But and the lesson of this paper is basically that if you don't use discontinuous metrics like accuracy basically measures if the answer is correct, but it doesn't measure intermediate steps. It doesn't measure if the answer was almost correct. Wrong is wrong, and this is a very discontinuous metric. But if you measure with more continuous metrics, the emergence goes away, or even better, it becomes diminishing returns. So this is why I wanted to talk about this, because this is usually what gets into the press, but what actually happens under the hood is more like this. If you measure well, you don't have this scary emergence. Okay, and this one is about LLMs, the pure language part out of this, and I will just spend 5 more minutes to talk about how to extend this to multiple modalities, because I am quite sure that many of you who study physics are not that interested in language, but would have some spectrogram data, would have some images that they would want to process with a transformer decoder or encoder, and the question is how to do it. So we have learned about having having an autoregressive transformer can process input text and can produce the next most likely token given on that given these language tokens. So if we have an image now as input, how can we give it to the model? First, we need to somehow come with an idea of how to represent images as vectors, because as long as this is a vector transformer can work with it. We can apply self-attention, we can apply for neural networks, and we have discussed of how via tokenization we can transform text into vectors, but how to transform images into vectors? I would say it's even easier, because while text is very symbolic, here, what is an image? It's basically a tensor, and to map a tensor to a vector is, I think, easier than mapping symbolic stuff to vectors, because symbols are discrete and vectors are continuous. So what we can do here is split the images into patches and then have a linear layer train. So we have a linear learned mapping to map us this patch into a vector. And if we learn this layer jointly with the transformer, we can just, let the transformer apply on this as well, right? And what usually happens is that if you have a language model trained on a lot of language and has read Shakespeare and archive papers, then if you want to give it text that talks about images, you somehow need to find that text that talks about images. Where do you find text that talks about images? On the internet, on image captions. And I don't know if you have ever programmed a website and have written an image caption, but how lazy were you? A picture of me, dot. Right, that's how we write a caption on the internet. So captions on the internet, so paired text and images are containing text that is super boring, linguistically undiverse. I mean, think of Shakespeare and think of the image caption we write. It's a difference, right? So the idea is to train a transformer just on language and then extend it to the vision modality by training these linear layers that will map, hopefully, the image vectors as close as possible into this text space, but it's hard, of course, to map images to the text space. So, and the transformer will get the text, but will not get the images very well. So a solution here would be to just train a few adapter layers, so that just to append some few learnable parameters to your transformers that will give it the capability of understanding the images, but you freeze basically all the parameters that you have had in language training, such that you don't have this catastrophic forgetting phenomenon of forgetting Shakespeare because you're now training on boring text that is captions, image captions. Yeah, cool. And now if we have done this, can we do it like this? Can we now train on just images? And here you can imagine that it's not the word mountains, but it's a class that we're doing image classification that will encode the class mountains. I think kind of yes. Yeah. So if we have a way to process map a modality to vectors, we're fine. We can do we can apply a transformer to it and think of audio, which you can represent as spectrograms, and spectrograms are images, and yeah, you can basically apply these things on kind of any data you imagine. And just to make the last bridge to diffusion models need, so if you want to produce images from text, you need a way for the diffusion model to encode the text. And it's a little bit hard to train image generation and text understanding at the same time. So what diffusion models do, they just take an existing encoder that was trained on lots and lots and lots of language and take these final representations, all the final representations or just use representation of the CLS token, and use that to represent the image and condition the diffusion model image generation onto it. And that's how you generate, make a text to image diffusion model. Great. So now the final slides basically are to remind you that models are cool, but I hope that what has happened since 2020 with all this prompting and all this collection of extra instruction and this collection of human feedback, that data is very much important. The quality of the data is what makes, I mean, models, you can change a lot of things into them, you will get some gains, but most of the gains you get to data, data, data. And I would like to tell you about Gopnik's parable of stone soup AI, which is a point that Alexei Efros did at the HLF using the idea of Alison Gopnik, which is a renowned cognitive scientist. But to make the point of a stone soup AI, do you know the parable of the stone soup without AI in it? Well, the parable sounds like this. There were some travelers coming to a village, and the travelers were hungry and they were asking for some food, but the villagers said, no, there's some famine here, we don't have any food to give you. So the travelers said, no problem, we will make soup ourselves, namely stone soup. So they just took a few stones, put it into a pot of water, started to boil it, and boiled it for a couple of minutes, then tasted it and were like, this is a very good stone soup, but if we would just add just a little bit more carrots, do you have some carrots? Yeah, okay, great. The villagers brought some carrots, put the carrots into the stone soup, then they tasted, the travelers tasted it again and were like, yeah, this is almost the perfect stone soup, just a few more chicken and some tomatoes. And then the villagers brought chicken and tomatoes, and then they all ate stone soup, right? Well, And this is a little bit what happens with AI too. Namely, tech execs come to a village and they will say, we will make this amazing AI with just a few magical algorithms with gradient descent, transformers, next token prediction, and so on. But it would be so much better with more data, internet scale data, and cleaner one. And it would be even more magical with human feedback, with a lot of human annotators sitting around and doing very badly paid work. And it would be even better if humans would learn to ask the questions in the correct way. And this is prompting. So now the villagers say that, wow, it's magical AI from just a few algorithms. And this is what I would like to end with. And yeah, thanks for your attention. If you have any questions, I'll be here in the break. And I think then you will continue the lecture as usual. Thanks.